Muy bien. Continuando con el rol de exposiciones para el día de hoy, a continuación vamos a presentar al doctor Junior Silva. Él es investigador de la Universidad Estadual de Mato Grosso do Sul. Tiene experiencia en física de la materia condensada, trabajando principalmente con vidrios y cristales dopados en tierras raras y metales de transición. Convertidor de energía para celdas solares de silicio, refrigeración óptica y espectroscopía de lente térmica. El día de hoy nos presenta el tema titulado Optical Refrigeration, a Cooling Interaction Between Light and Matter. Next, I present Dr. Junior Silva, researcher at the State University of Mato Grosso do Sul, has experience in physics of condensed matter. And today he presents us with the subject entitled Optical Refrigeration, a Cooling Interaction Between Light and Matter.
Okay, can I share the presentation?
Yes, please. Can you see? Yes.
Yes.
Okay.
I don't know if I start from the beginning.
Yes. See. Now you can begin, doctor.
Okay. So here I listed some moments of refrigeration in human history. If you give a click, please. This first moment was a long time ago, 1700 before Christ. People used to put ice in some houses and sell it. And after that, in 1748 AD, William Cullen was the first one to create artificial refrigeration. And the next one was Jacob Perkins, the father of refrigerator. In 1834, he was granted with the first patent for vapor compression refrigeration cycle. And this technology is a technology we still use today. This technology can go to a minimum temperature around 10 under 0 Celsius degree. Vapor compression refrigerators, this kind of technology, have a maximum efficiency of approximately 30%. Okay, but the problem with this kind of technology is that it uses harmful gases that cause greenhouse effect and destruction of the ozone layer. So we need to go to another kind of technology. Another important information we need to keep in mind and see that this is a problem, this kind of technology for our planet. 15% of all electricity produced in the world is used for cooling process, and this should increase in the future because people want more comfort, and it's necessary for equipment to keep the food okay for people and the population increasing and so on. Can go. Okay, and another information I commented before, 45% of energy consumption in homes and commercial buildings is related to refrigeration system. This is a lot. And the energy that we use is still 80% used on Earth is from fossil fuel. This is data from 2015. And we need to keep focusing in preserving our environment, and optical solid cooling can be a good alternative to cleaner cooling production systems. I guess I stopped it here. But how this system works, we need to go back to Stokes in 1852. And Stokes said that we can, when we pump the material, we excite the electron, and when it returns to the ground state, it emits light with lower energy, like in this spectrum. Here is a real situation, cerium Eg crystal. We pump that line, as we can see in the figure. It's the pump of some lasers, and we pump the material with higher energies, and we can see the luminescence with lower energies, as Stokes said before. But Rama Experiments 1928 observed a different thing. Use, for example, hypothetically, use a green photo, and after that, the material returned a blue one. This is hypothetically, but what I mean is we use energy, and the material gives back higher energy. Where is this energy coming from? And after these observations, Peter and Pringsheim had an idea. For example, here it's a real case. We can see the absorption spectrum in that dashed line, and here two pump was used to generate this blue and red spectrum of emission. The blue one was generated exciting the material around 400 nanometers in the blue region. And after that, the material was excited at 700 nanometer between red and infrared. And we can see the emission at the same place, the red curve. And so I used one energy to excite the material, and I got from this material higher energy. Okay, and Peter Pringsheim in 1929, you can go to show the picture of the Peter. I can go forward. Okay, and Peter, this guy that should be here, this one, he thought 1 year after Rama Experiments and said, well, we should be able to cool matter. And this happened. When this happened, you can go to the next slide, please. Okay, this happened in 1981 in a gas, with CO2 gas, okay? 9 years later, in a liquid, rhodamine 6G, and 5 years later, in a solid, ytterbium 3+ ZBLAN glass, okay? It's a fluoride glass, similar to that one Odon wants to synthesize, okay? And the guy that saw this effect was this man. Here is a picture of the glass and how this worked in this material. If you go a little bit forward, here is this one. Here we can see this spectrum of the absorption spectrum and the emission spectrum of ytterbium 3+ in this glass, ZBLAN, this fluoride glass. So the red one is the absorption, and the blue one is the emission. And the cooling region, where the place where you need to pump the material to see cooling, for the material to cool, you need to pump it from the top of the ground state, like in the energy levels here, from the top of the ground state to the bottom of the excited state. So from the top of the ground state to the bottom of the excited state. And this system will try to get the equilibrium again, and will absorb phonons from the lattice of the material. And these phonons go out of the material through luminescence. And after he goes down here in the ground state, he absorbs phonon again. And this cycle cools the material, okay? And this way works the solid state cooling. After this experiment and this observation in 1995, people thought, should we cool semiconductors? Is that possible? If it's that possible, they started to do some estimations, simulations, and they realized that they could cool to approximately 10 Kelvin. That's amazing, the minimal temperature. And several applications could happened from this achievement. And people tried 2 years later in this double heterostructure, gallium arsenide, gallium and phosphide. But they did not succeed. Okay, here we can see another picture, a real picture. This one, a real picture. They need to put this dumb lens on the material because the refractive index is so different, the air, that the luminescence cannot escape. So you use the dumb lens only to make the luminescence escape of the material. But after this, in 2013, some researchers from, let me remember, I think it's the next, if you click one more, from Singapore, yes. From Singapore, these guys, they claim to had observed laser cooling effect in a semiconductor, cadmium sulfide. But they cannot reproduce this experiment, and nowadays they have been very criticized for other researchers. Next one. This table put together all the materials that present laser cooling effect. And there is one that's the best one, is that fluoride crystal. If you click again, we can see it. Oh, this one. This one is the best one. And many papers, many studies were done in this material. You can go and you see the next slide, these papers. Yeah, this one. This was a great achievement. This crystal cooled to 110 Kelvin. Okay, using ytterbium 3+ ions. This the result was an exciting result. And the authors, 2 years later, they decided to give a big attention that we were in the cryogenic temperatures with a solid state. What's another great achievement? Can go forward. Yes, and in 2016, this material cooled to 91 Kelvin, which is under 100. The first time the solid state cooled under 100 Kelvin. And in 2018, this material was used for the first time in a real situation to cool a sensor. And we can see the setup here. We can see the cold finger, the sensor that was used. It's a sensor used in a very known Fourier Transform Infrared spectrometer. And the sensor was cooled to 135 Kelvin. And you can see there the crystal being used for this refrigeration situation. The next figure here, it's how they cool the crystal in a real situation. Because when we study this material, you just use the laser to go through the material. In this case, they use the laser to get like a trap inside of the material to go to total reflection inside the material to be completely absorbed by the sample, the light. And here we can see a graph using the crystal and using liquid nitrogen as classically is done. There is a region here from 800 to 1,400. That's okay, but the other part is not okay. We should cool more, okay? But this was the first experiment. And this experiment made the first page, perhaps the most famous laser magazine in the world, laser focus world, this experiment made the first page of this magazine. And the man behind all this research is this one, Mansour Sheikh Bahai. Okay, a summary of the most important achievements we can see in the figure. When people saw this effect in 1995, after that they got some improvement in ZBLAN, and they made some estimations how far they could go. And they saw that they could go to close to the boiling of liquid nitrogen, and compared with another technologies like thermoelectric coolers. And today, the next figure will show, yes. So 20 years was taken to get close to the idea, close to the estimations made in 1995. Here with blue we can see ZBLAN, and the red one we can see the results of the crystal, and we can see Pertier coolers here, below, and cryogenic below cryogenic, close to boiling nitrogen. Okay, that was a very nice publication recently, 6 or 9 months ago. People observed laser cooling of a thermal-doped silica glass. Never before people had observed cooling an oxide glass. That was very nice, because in my opinion, I think this material cannot go to cryogenic temperatures, but can be a very interesting material for daily cooling applications, like our refrigerators, air conditioning. Maybe perhaps in the future we can have a laser and the silica glass producing our cooling systems. Okay, next one. Here it's this table is to compare the technologies. For example, in this column, it's a pink color, more or less. We can see the characteristics that's required in cooling applications, and this blue one is the characteristic, is the different technologies. So, for example, solid state is something required. So, optical refrigerator, yes. Thermoelectric coolers, yes. Mechanical coolers, no. Vibration free, yes for optical refrigerator, yes for thermoelectric coolers, moderate for mechanical coolers. Reliability, high optical refrigerator, high for thermoelectric coolers, and moderate for mechanical coolers. Below 180 Kelvin, yes optical refrigerator, no. This is the main competitor of the optical refrigerator, and yes for mechanical coolers. Efficiency, okay, but this can change for optical refrigerator, and I'll talk about this later. And no for thermoelectric coolers, and good for mechanical coolers. And cool below 60 Kelvin, no for optical refrigerator, but this can change too soon. And thermoelectric coolers, no, and mechanical coolers, yes. And there is one more thing that optical refrigeration is so special. Optical refrigeration is the only way to cool electronics in space to cryogenic temperatures, and that's why this technology has get the attention from some important agencies in the world, like Air Force in the United States of America and NASA, for example, that are supporting this kind of research. So, but some people from spectroscopy area or science materials must be asking themselves now, how can I get how can I get this material that can cool? How can I find this material? So this is a map. Dr. Marcus Helling, he made this map, and we can see here, for example, there is this straight black line. Here we can see in the y-axis maximum phonon energy, and here in the horizontal axis energy of first excited state. Okay, so our material needs to be below this straight black line. We can see above the ions here, ytterbium, erbium, thulium, ohmium, and so forth, and so on. And here we can see the families of materials. For example, oxide family present higher phono energies, maximum phono energies, and after that comes going down, fluoride, chloride, and so on. So we need to put our material here to observe cooling. Of course, when we go down, there is some problems with these materials. For example, fluoride and chloride, the most of them or part of them show hygroscopic characteristics, what is not good for laser cooling. But it's easier to see laser cooling of these materials. And we could, you guys could tell me, well, it's easier to see cooling with ytterbium 3+. And the answer is yes. But if we, the next picture, with ytterbium, we can go only to 5% of cooling efficiency. But with cerium, for example, we can go to 30%. And perhaps we could compete with vapor compression refrigeration system. So we have to balance this. And here's some publication of our group. This one's from the last year, our collaboration with the University of Michigan, USA. This material, we saw laser cooling for the first time. Go a little bit, click one more. Here, the first time. And this is an interesting candidate for radiation balanced laser, this material. Why? Because this crystal, doped with ytterbium 3+, presents a high emission absorption cross-section. And you can ask me, why? What is this radiation balanced laser? If you go a little bit more forward, yes. This works this way. We pump the material in the cooling region, so the material cools and emits light. And we can get this light put in a cavity, and we can have the stimulated emission, so we can have laser. And in this case, we will have a material that produce laser and cool itself. If the material works this way, we can improve significantly the laser beam quality and have lasers, continuous waves, lasers with output of multi-kilowatts, which is a lot. Okay, that's why there is a great interest in this, and some agencies in the United States, it's putting a lot of, it's supporting a lot with a lot of money, this research. Okay, here is another one, 2 years ago. And in this paper, we had the participation of Mansour Sheikh Bahai, which is the leader of this area in the world. Okay, the next two, yeah. In this work, we studied that best material for laser cooling, but we studied two cerium 3+ EI crystal. Here we can see that if this material goes straight in this dashed blue line, this material would be cooled, but it turned. And why this turned? Because the quantum efficiency, that is one of the parameters required for cooling, was okay, was 99% in this material. And the background impurity was okay, because was 1.2 times 10 to -4 centimeters to -1. So the problem in this material was the excited state absorption, which makes of this material a non-laser material. It's okay for white light, and it's well known, this material for white light, but it's not okay for laser. And is not okay either for laser cooling. Okay. One more. Wait. Yes, but this material taught us something. For example, if this could cool, would go to a cooling efficiency of 15%, what is 3 times the Thermo3+. And a minimum achievable temperature would be under liquid nitrogen. That's why I told you guys that we can change cooling efficiency for this technology and the minimum achievable temperature as well. But you can tell me, well, can you solve the problem with the excited state absorption? In this system, probably not. But taking this cerium-3+ ion and putting another matrix, yes. That's why we still have hope. And in my presentation, the guy that was the first one to observe this cooling effect, Richard Epstein, he already co-founded enterprise to commercialize this kind of materials, this new technology. Thank you very much for your attention, and sorry for the problem at the beginning.
Thank you very much, Dr. Junior Silva, for your presentation. Any questions from the participants? ¿Alguna pregunta por parte de los participantes?
You guys can do it in Spanish. I'll try to understand.
Okay.
If you ask me about superconductivity to cool the material to work as a superconductor, yes, we because it can go below cryogenic temperature.
Okay, ¿alguna otra pregunta, alguna otra consulta? Anyone to have other questions? Pueden levantar la mano directamente o prender su micro para poder hacer la pregunta al doctor.
Bueno, parece que ya no hay más preguntas, Medina. Bueno, okay. Thank you again, Dr. Silva, for your participation in this event.
My pleasure.
Gracias, muchas gracias entonces a todos los participantes. Y bueno, creo que por el día de hoy es todo, ¿no? Medina.
Sí, por el día de hoy, el día 1, esas son todas las presentaciones. En todo caso, nos estamos encontrando el día de mañana a las 10:40 horario peruano. Igualmente, cualquier cosa desde el correo del comité oficial se va a estar haciendo el laboratorio y nos estaremos encontrando el día de mañana. Entonces, muchísimas gracias a todos por la asistencia.
Sí. Gracias, muchas gracias. Estaremos continuando el día de mañana entonces. Nuevamente gracias al doctor Silva por la presentación y por la participación en este evento y gracias a todos los asistentes también. Hasta mañana.